Welcome everyone to the INQA seminar. This week it gives me great pleasure to introduce Marcin Dukalski from Aramco, the Global Research Centre in the Netherlands. And Marcin will talk to us about early applications of quantum computing to subsurface imaging. Marcin, over to you.
Great. Thank you, Paul, for giving me the opportunity to speak, and also for inviting me to your beautiful and lovely conference in Innsbruck last month. With this presentation, I would like to take to go a little bit deeper than what the time allowed in Innsbruck, and hopefully convince many of you that there is actually the world of geophysics and quantum computing actually have quite a lot in common. And I'll try to illustrate with one of those things that we are quite proud of accomplishing in the last couple of years. So this work is not by any means entirely my own. We have been supported by all of these lovely people. My special thanks go here to my dear colleague and friend Diego Reveta and Apostolos Kontakis from our office in Delft, but also people from the University of Delft, so Professor Matthias Müller, Stanrik, Benjamin, and Sinru all contributed to this work. We had people from the Dutch National Lab and Maastricht University, that's Niels Neumann and Frank Philipson, and of course we received support from the vendors. And one of those things about working at a big company is that you have to have certain restrictions about mentioning names of other companies. So unfortunately, I'll leave it to you to figure out who is working otherwise. So what this talk, I mean, I've been following the seminar, and then I always enjoyed watching the presentations and learning about what other people are doing. And I hope with this talk to give you a bit of an end user angle on quantum annealing. I do have a background in quantum computing myself, but after my PhD, I went and started working in the energy industry nearly 10 years ago. And about 5 years ago, I made my move back. So my perspective is more of the okay, we now have quantum annealers, we have quantum devices. What can we do with this such that it impacts the business? And in a sense, this talk will be about 40–50% focus more on the motivation, on like what process did we go through when we were picking up a problem that we thought we want to tackle first with a quantum computer, and then tell you what that problem is, and then of course close a little bit of a with an outlook. So for the motivation, one of the biggest challenges that have to do with actually trying to do something useful with a quantum computer is to identify the use case. I heard a recent interesting quote that the use cases are the new gold as far as quantum computing is concerned, because finding something that is hard enough and at the scale that is relevant and that doesn't have a good classical algorithm to solve it with, or where the quantum approaches could already benefit you, that's quite a tough problem to do. And it's not so much difficult from a technical point of view, but also from a people point of view, because you have to engage with a great number of people, try to find experts in different fields and their disciplines, and study problems together and find out if a quantum computer will be something that could help today. And once you work with a quantum computer, you have to also worry about things like architecture, its size, its scale, whether input-output would be a problem. And then finally, what we have learned from this in the process as well is that we'll just always be hybridizing things in some shape or form. And well, depending on how this mini questionnaire goes and all the questions that go behind that, this becomes a little bit of an iterative process with a problem holder to really identify the use case that works best. When it comes to use cases, perhaps, I owe you quite a bit of an explanation of what is it that we actually do. So Saudi Aramco is the oil and gas company, is the biggest oil and gas company in the world. And what the corner of the company that I'm working in is in advanced computing, which initially was in the field of geophysics. Geophysics is one of the biggest consumers of high performance computing in the world. And it simply has to do with the fact that the process of mapping out the subsurface is an incredibly computationally intensive task. But this doesn't only go for things like finding oil and gas, but also storing carbon dioxide or hydrogen for as we move into the energy transition and advance there. Also find plumes of heat where we can drill geothermal wells, and of course identifying mineral deposits as we're electrifying our economies. All of those fields are part of geophysics, and there's a lot of interesting mathematics involved. If I were to describe, what we do with a single picture, it's basically our job is to make these kind of pictures. This is a what we call an outcrop. It's basically a lot of geological layers that have been thrusted up by some kind of tectonic or otherwise movement, such that we get to see it with our bare eyes above the ground. So you can see all of those little layers, and there's quite some contortion as well on those rocks. This is the stuff that we would like to image as it sits hundreds of meters or kilometers below the surface. And the process is very similar to performing an ultrasound. However, with ultrasound or medical imaging that you see in general, there are quite a few things that make things a little bit easier. For one, as you can see in this picture, the ultrasound gets sent into the body. It scatters of 3 possible media: air, liquid, or bone. There's literally nothing else, and it's collected back by the receiver. Immediately, image gets generated practically in real time, and there's a person that can interpret it as you go. When it comes to geophysical imaging, this process can take many months, sometimes a couple of years. It starts with acquisition, either at sea with a big boat towing behind, kilometers of cable with receivers, acquiring gigabytes of data, or hundreds of gigabytes of data sometimes per day. Same goes on land, where you have to also deploy now those what we call geophones, put them in the ground, and send waves into the subsurface. That process alone is several months and petabytes to tens of petabytes of data. The data looks, after some data pre-processing, looks what you see in the middle picture, and we're trying to converge that the wavefronts that have been scattered and are measured with a certain time delay relative to when the wave was initially sent into the subsurface. You're trying to convert this time information into a depth information during the process of imaging, and that's where we're figuring out what the geological strata sits. Albeit that only happens at the stage of interpretation, where somebody with a geological background now and understanding of the area can actually put some quantitative attributes. All in all, this process could involve tens, if not hundreds of people if you count acquisition, and can take quite a bit of time. We also don't have this advantage with medical imaging, where they can image their patient from all possible angles. We can only access things from above, which makes the problem significantly more complicated. So the challenge that we're always facing, and that's why high performance computing is very much at the core of geophysics, is that at any point in time, the moment we get more or better data, or now algorithms that are better prepared at handling those data or letting go of certain assumptions we made, or we get the latest developments in high performance computing. That shaded area, the intersection of this three set becomes bigger, and we get better feeling, more information about what the subsurface actually contains. And that's particularly important in fields where gas storage, for example, is involved, because you want to know how much of what sits there. That's additional information. Now, when you try to do, I'm a theoretical physicist by background, so for me, just making things quantum, you just replace a Poisson bracket with a commutator, and you start talking things being quantum. The problem from a high level perspective remains the same, but now, of course, quantum data means putting things in a superposition. Quantum algorithms, we have a bit of a shortage of when we look at both digital or gate-based and computing. And of course, we're still waiting for the highly performing quantum computers. But for the purposes of this talk, we're going to be narrow it down to just quantum annealing. And the goal or the definition of success is, let's do something interesting and let's see if we can get things on par with a classical solver, and that's already going to be great. So the process of just data processing and getting towards an image, so the middle bit that I discussed earlier on, is broken down into a great number of steps, and we looked extensively at all of them, looking for a useful, hard enough, yet small enough and business relevant problem. And we have found one, and it has to do with understanding what the very near surface of the subsurface looks like. Because the near surface is subject to things like hydrology and weather and all kinds of human interventions. It's quite much more varying than the depths that go below 100 meters or so. And not only this is just one module that we will be working with, but we identify a subroutine within it, which works very well with a quantum annealer. So the way things, to jump things into a little bit more technical, the way things work, we have those vibro-sized trucks which send pulses, the waves into the subsurface, and every time they meet an interface between two geological strata, here in gray and orange, the part of it will reflect and part of it will transmit. And by the time it hits the receivers or geophones, you're going to pick up that little wiggle here in green, and there is a lot of those wiggles that you measure in a seismic signal. This is just an example of seismic data, and I circled one of those wiggles, and that's where we're going to focus for a better part of this talk. And the reason why we're doing quantum annealing is because we really value remaining in the global optimum, and it's not so much that it is a better solution, but it's simply a truer solution. If we can significantly increase the confidence that we have performed some kind of an optimization problem and found a global optimum, then that cascades through this entire workflow that I showed you earlier on, and can significantly improve our seismic image. This is quite different from when you're comparing it to use cases, for example, in logistics, where you're just looking at, or scheduling, where you're just looking at the configurations of things and you're just getting a 10% improvement. Here, it's a difference between getting it absolutely correct and introducing some additional uncertainty. So on the right, you see what a typical seismic image looks like, and I'm going to flip back and forth and just pay attention to where the white arrows are. You have those strips of white, horizontal strips of white and black pixels, and you will notice that suddenly, as I improve if I find an optimal solution, suddenly I have a very different feeling of what this subsurface looks like. Either geological strata become continuous, or their shape changes, And if inside this porous rock there is liquid, this being oil, gas, or water, or carbon dioxide for that matter, uh, depending on the slopes of those lines and whether they're continuous or not, that means that the accumulation of all of those fluids can geographically shift on the scales of kilometers, which will have an impact on all of those decisions about, for example, drilling that you will make at the surface. So let's talk about our use case. So that's residual statics. So this is, I believe, a picture from Dover. What you see is, if you're just sitting on the surface of the big plane above, you don't know that there are all kinds of caves below. And here, because we have a cliff, we're able to see from the side, and we say, okay, clearly there's a cave structure underneath what otherwise seems like a very, very nice and green flat area. And that's what geologists call karsts, and they have quite a big impact on our seismic signal. Here, this is a data taken from a synthetic model. What happens is that when you send waves into the subsurface and they have to travel through a pocket of air instead of traveling through a pocket through rock, their speed is reduced by a factor of about 10. Wave velocity in air is about 300, in rock is about 3,000 meters per second. What it does is it makes the seismic signal quite choppy. And if you pay attention to the black and white picture on the right, which we call a seismic gather, this is the difference that those shifts can make. And all of that uncorrected for choppiness in the seismic image will affect not only what you think the shallow subsurface is, but everything deeper down that I showed a couple of slides before. So it's very important that we try to correct this. And the way the problem of correcting this is formulated is that what you may have seen here is that those seismic signals form a little bit of a hyperbolic pattern. So we correct for that hyperbolic shape such that now the signals are flat. And if there's a little bit of choppiness on it, we try to align them relative to each other. And we use a very simple mathematical formulation for this, is that if things are misaligned relative to each other, then they will create a large number of small wavelets or pulses of sound. And if they're correctly aligned to each other, then they create a fewer stronger ones. And when you square this, when you square the amplitudes of the sum of those signals, or what we call traces, if they are aligned, the square will give you a bigger result than they are misaligned. So the squaring is very important, and that's why we call this thing a stack power. Stacking, geophysicists call stacking basically adding things together, and power because we're taking a square. So we have this combinatorial optimization problem where we have to shift signals relative to each other, and we'll literally be trying to align hundreds, if not thousands, of those traces relative to each other. And because of the nature of the signal that we are measuring, and this is just a picture for two signals relative to each other, if you're shifting them past each other, you find this very multi-modal objective function with a global maximum and plenty of local optima to be stuck in. So this was a very, very appealing problem to try to tackle with a quantum annealer. And the way to do this was to first discretize the problem and choose a given set of times that you will be shifting by. And when you do that and open up the brackets, you realize that your objective function is actually boils down to calculating cross correlations between any two signals that have been shifted by some amount, and there is that delta in front of it, which denotes a discrete variable of whether a given shift was applied, and that cross correlation was added to an overall stack power or not. And of course, the annoying thing about this is that discrete variables are make for a Potts model or a DQM,
and they are not Ising models. So step one would be to represent those discrete variables in terms of multiple qubits, either using a one-hot or a standard binary encoding. We can, of course, use gray code or domain wall. In addition to that, we're going to talk about this in a second. But other than relative inefficiency with using a one-hot encoding, you also have to worry about the fact that you have all of those qubit configurations that you now have to suppress, and they are different for one-hot than domain wall encoding. But the bottom line is we have to add constraints, and that's usually not something that you would like to try. However, we did and failed, and then had to fix this. We also tried using standard binary or gray code encoding, and we'll show you that in this case, it's not an approach that yields a sort of a QPU native formulation or an Ising model. So the one-hot encoding, we're simply replacing those discrete variables with a given qubit now being 0 or 1, and we add the penalty term, which suppresses all of those unwanted configurations. And quite quickly, you realize that we're always going to be working with graphs which are fully connected, and the number of vertices or variables on this graph is simply a product of all the signals or traces that you're trying to align and all the shifts that you decided to discretize your problem with. And both the I'll show this here if this is part of your recording. So both the cross correlations between any pairs of traces, of which there's only a quadratic amount, as well as the penalty terms get mapped onto the edges and vertices of those graphs. And what ends up happening is we can now solve the problem, and its situation is quite similar with domain wall encoding. And we've tried it and presented this work earlier this year, but I don't think there is a paper yet. We'll be working. When it comes to standard binary encoding, we have to be aware of the fact that if we want to shift a signal, that simply amounts to going to a Fourier domain and multiplying it by a phase factor like the one that you see on the screen. And that phase factor could be simply represented by a product of like this big polynomial. So just to give you a quick example, if we want to have I realize now that there is, I think, a minus sign mistake, but it doesn't change the argument. The point is that if you, for example, want to say, okay, I'm trying to shift a trace with 6 time steps, that corresponds to a binary number which is 110. That basically means you have to activate or deactivate a shift of you have to deactivate a shift with 1, you have to activate a shift with 2, and activate a shift with 4 time steps to jointly get 4. What this basically means is that in order to create that shift of up to, in this case, 7 time steps, you need a cubic polynomial in the binary variables, and because you need to be shifting 2 of those traces in the objective function, you're at 6th order. And that's, of course, not a quadratic unconstrained binary optimization problem. So the step that you inadvertently need to do is you have to quadratize. Once you quadratize, you add more variables, and you also add constraints. And we found out that it's clearly disadvantageous. So on the graph on the top right, we compare the maximum problem that we were hoping to solve with a binary encoding or the indicator or one-hot encoding. And we kind of hit the same boundary, which is given by that straight line in the space of the number of shifts and the number of traces. With the one-hot encoding, we also noticed that the bigger the problem, especially as we're trying to check that we have a greater and greater number of shifts, so a wider search space, more and more often we were getting results that don't make sense. So in the top left, you see a misaligned synthetic signal where the solution is quite obvious, just a black line, white line, black line. Whereas the best solution that we were able to get is the one that you see here. Blue means that constraints were observed, and the red that they weren't. And we were a little bit puzzled by this, why this happens so much. But so we'll cover that in a second. But one of those things that also we tried doing is use like a greedy algorithm on post-processing to find a better solution, but we weren't able to get it to scale at the stage to a number of traces and shifts we wanted to apply to in practice. Now, why would we want to violate things so much with this one hot encoding? It's quite simple. If you take 2 copies of trace number 2, then you know that the solution 00010 basically shifts the middle trace up by 1 unit, as you can see here. If the solution 1000 will shift it by 3 units upwards, so for example, something like that, and that sort of increases your alignment. But what mathematically this means is that you're basically adding trace number 2 twice, and you really don't want that. So you in principle you have a mechanism in your mathematical formulation or in your problem itself, which favors violations of one hot encodings, and that's definitely something that we wanted to avoid at all costs. I'm realizing I'm going a little bit over time here. This is taking more time than I wanted, so I'll accelerate a little bit. The problem with adding the constraints and increasing the penalty term is, of course, the fact that after renormalization, we're just solving a almost random but very well constrained problem, and at some point you cannot find a good range of those minimum and maximum penalty parameters, even if you know what the solution is, which kind of defeats the problem. But you don't have that problem if you just want to do this with the binary encoding for just a shift or no shift, as you see on this example, and about 170 signals, and aligning them is the maximum that you can do with the current device. So what we have done is we combined it with this method of Okada, which is the binary partitioning of the POTS model, where we iteratively pick always 2 of the possible shifts, and we store the best outcome, and we always pick a new combination of shifts for the new iterations, and we go back and forth doing that. And when you do that and you try to sort of visualize the result, and this is roughly at the real time at which you will be solving this problem by bouncing the problem back and forth between our computer here in Delft and the machine in Jülich, where every single iteration you basically ask yourself, is there a better way to align those problems? And after about 100 or so, you're going to find a beautifully aligned result. Whereas in this case, we knew what the solution ought to have been. So, now it wanted to work. Okay, great. So what we did is we applied it to an industry standard seismic data set, where we have all of those gathers with tens or nearly 200 traces or so, and we started aligning them one by one, basically trying to get that correction after we take away that hyperbolic shape. And we compare this to the tool that we normally use, which is like a mean field theory approach. And this is the input data. There's some misalignment in it. This would have been our classical solver, and this is what we got with a quantum annealer. So we got about a 15% improvement over this particular gather. There was another one where we got only a marginal improvement with a quantum annealer. There are some where the improvement wasn't that much bigger. We just repeated this thousands of times and processed about 10 gigabytes of data doing that, and sent, I think, something to the effect of hundreds of thousands of jobs to the annealer. And we've then compared our result all those shifts that we have collected, we inverted that for a map of the subsurface. Here we knew the ground truth because the model was synthetic. So that's what you see here on the screen. And here in gray is what our algorithm predicted the shifts would have been. So we were able to replicate the quality of the solution that we got with a standard classical approach, with a little difference here, which we're in the process of figuring out. But it in principle boils down to the fact that this was the area where some of the gathers actually with the quantum annealer, the solution was a little bit worse. You can see that by the number here, by the way, in the bottom left. We're trying to figure out if it's a scheme matter of how we set this up or something about data preprocessing. But statistically speaking, we got something like a 3% better result. And we basically plotted the difference in the stack power for each and every single one of those small data sets. And seeing that there's more of the net improvement is bigger than the net decrease in quality of the solutions between the classical and the quantum approach. So that gave us a lot of confidence. And what we have been doing since then that I think of beyond what I can cover in a single talk is that we've actually built now a software release that our colleagues in the headquarters can use and play with. One of those things that has an impact on the overall computation time is how much time you spend in a network by sending the problem back and forth to a quantum computer. You can see that on the quantum computer itself, we're spending a fraction of a percent of the time, but while on the internet, we spend 98% of it. We've been able to reduce that 98% by about an order of magnitude by being a little bit clever with how we group submit things. We also figured, we built our own hybrid solver so that we are more confident with, all the optimization being purely quantum. I mean, let's not forget that this is still a research and development project, so these are the kind of things that are important. We've taken on an interesting project when we looked at, can we, based on the input data, figure out if this is difficult enough for a quantum annealer, or is this one of those cases that a classical solver could do better? This is still ongoing work. We're now gearing up to start working on field data, and you remember this is where we're starting to enter into like petabyte regimes. So we're ambitious, but petabyte is a little bit far. So 1 terabyte of data that we would like to find a map of the subsurface in an actual, from an actual geophysical measurement is what we're aiming for before the summer. But we also used a couple of other use cases, like trying to find the shortest path through the subsurface, because that's something that we use a lot when we're trying to find those velocity models, which help us convert when the signal came from to where the signal came from. And we're of course looking at other architectures and how to solve similar problems, for example, using the neutral atom and the Rydberg blockade regime. Finally, I wanted to say that if you're interested in the kind of work that we do, we currently have an open position for somebody with a few years experience after their PhD in the field of applied quantum computing, especially adiabatic quantum computing, quantum annealing. But if you're for example, a professor looking to do a sabbatical somewhere, or a PhD student postdoc looking for a research visit, come on over. We were always very happy to have people over. We also offer several internships for master students to do their master's thesis or some other industrial experience afterwards. So do let us know. This QR code should take you to a LinkedIn post with the job ad, but you can otherwise always contact me if you're looking for an industrial collaboration. With that, I would like to thank you and give it back to you, Paul.
Good, thank you very much, Marcin. Very interesting stuff, and great to hear that there's some real applications out there for which quantum annealing seems to be making a difference.
It is, yeah.
I'll open this up for any questions from the audience. Well, maybe I can start then. So this I didn't quite understand how this 3% improvement was quantified. That's your scale factor.
Yeah.
In your stack power. That's the
So it's a rather crude estimate. So what we effectively did is we calculated a median. Okay, so first we calculated the quality of the solution from a classical solver or the quantum annealing enabled solver, and that gave us the stack power. Then we took a difference. We calculated the difference for each and every single small data set like this one. So here you have the input of 0.61, the output is 0.066 or 0.041. So this is the case where a classical solver gave us a better result by about 0.025. Okay, so that was one data set, the data point, and that we created a histogram with 2,000 or in one case 16,000 of those data points, and then we calculated distribution, and we saw that predominantly the quantum solution was better because the distribution is tilted toward the positive end.
So I guess my question is a 3% difference in this metric liable to excite your higher echelons within geophysics, or is this just a sort of marginal improvement? I mean, I have no feeling for these numbers at all.
It was definitely enough to excite our management, because oil and gas is or geophysics is a very mature area. We've been doing this sort of stuff for 50 years, so the competition is fierce. There are tools out there that were developed to do an absolutely marvelous job. So the benchmark is very, very high. So if we come close to achieving similar results with an emerging technology, that's usually extremely encouraging. Especially at the scale that we were able to do it in. People don't believe that you can do practical quantum computing on very large data sets, and here we are. We did it, and this was our very first test. We are currently doing bigger tests and trying to benchmark things to see whether this is a case dependent, whether we got lucky this time, or whether we perhaps got unlucky, and yeah, we're still looking at it.
Maybe I just ask one more question then, seeing as I have the floor. So again, I'm having difficulty picturing in my head how you get all this masses of data onto, this 5,000 qubit, or is it 2,000 qubit, whichever one you're using.
Yeah.
So how does that problem get solved?
Right. That was the whole thing that worked out. So think of it in this way. So every one of the so we have a data set of about 10 gigabytes. That's about 16,000 gathers. So each gather is somewhere in the area of 1 megabyte worth of data. But from that gather, we're extracting a subsection of it, and then within this subsection, we're going to be extracting features, if you like, and that feature is simply a cross correlation between any pair of traces. So this way, we were able to. You can think of it as if you like to use some machine learning lingo, it's a little bit of like an encoder. We have taken a big problem and we've been able to reduce it now to a handful of variables or spins which interact with each other, and those interactions. I have it right here in the. The scale of those interactions are effectively the cross correlations from the data, and that gives us a single data point. And that basically tells us what is the weight on a given edge or vertex on the graph that we'll be sending to a quantum annealer. And by the time we get an answer from the device, we work our way backwards and know, okay, the signal should have been shifted by some amount.
Okay. Okay. Yeah, I think that's great stuff, Marcin. I mean, I'd be very interested to hear, as you were mentioning at the end, to what extent you might be able to do similar tricks with a classical optimizer. I think that's that's
in principle, you know, we have the same QBOs, and we can just run it with a NEAL package, right? And just do simulated thermal annealing, and we've done it. And in principle, as it currently stands, depending on the situation, we were anywhere between 10 times slower to 10 times faster to get to some quality of the solution. And that's what we're kind of trying to figure out. Which one of those data sets that we're trying to align the signals relative to each other, what makes one difficult and what makes one easier? Because by the time you need to repeat that tens of thousands or millions of times, which is what our next goal is, you can save yourself quite a lot of time, but by finding out which one is a difficult case or isn't.
Good. Any other questions from anyone in the audience? Well, if not, let's thank Marcin once more for a very interesting presentation. Thank you very much, Marcin.
Thank you very much, Paul. And thank you for having me again.
It's a great pleasure.